In this video, we're going to talk about 7.3 volumes of solids of revolution and the shell method. We just briefly introduced that last time at the end of our discussion from 7.2. So our objectives here are to find the volume of a solid of revolution using the shell method and to compare the uses of the disk method and the shell method and to decide when we should use each method. So we're going to go back to our completed notes over here and pick up right where we left off. We just finished our discussion on the disk washer method and said that we use that when we have representative rectangles that are perpendicular to our axis of rotation. Now we're going to say that sometimes it's more convenient for us to use the shell method, and the shell method is going to be used when we have representative rectangles that are parallel to the axis of rotation. So we're going to be using the idea of the surface area of a cylinder. Before we used the area of a circle and we stacked a whole bunch of circles next to each other. Now we're going to think of a whole bunch of cylinders that you're layering layers of cylinders on top of each other. So again, think of like those dolls that stack inside of each other, and you've got a little version on the inside, and then you've got a little bit bigger version of it that's got the same shape on the outside, and then the bigger version of that, and the dolls, stack inside of one another, but they've all got the same shape as you go, inside like that, and there's just a smaller version inside each of the bigger versions here as you open them up. Not really a great picture, but just think of it like that you've got. So if I have a big cylinder here, then I've got a whole bunch of little cylinders that are inside of it, like this. You could maybe think of the rings on a tree. Maybe would help you that you have the smallest ring and then the next biggest ring, then the next biggest ring, and the tree grows from the inside out like that. And that each of the rings is basically representative of maybe like a year or something like that. And you can figure out how old the tree is that way because the whole tree is the sum of all of these little cylindrical pieces that are represented by the rings like that. So, all right. So again, if we wanted to find the surface area, which I'll represent with a capital S that's kind of fancy like that for surface area of a cylinder, it's going to be 2 pi r h, where 2 pi r is the circumference of the circle here, the outside, and then I'm going to run that down the distance h, and all of these circumferences on the outside get added up, and that's going to tell me how much I have on the outside of the cylinder. Like if I wanted to make a cylindrical tube, how much material would I need because the inside is hollow here? How much stuff would I need on the outside to make that tube? That would be a surface area problem like that. So if we just take all of these surface areas, then I make another cylinder that's a little bit bigger than that has more surface area, and I do all the surface areas added together, I'm still going to get that same cylinder as when I did cross sections that were areas and I added all the areas together. So you'll see as we do more examples how this plays out. We have a new variable to consider here. This is this looks like a P. It's really like a row. a fancy looking P from Greek. And so that rho has to do with the radius there. And this H has to do with the distance to the axis of rotation. So just one of those is going to be the distance to the axis of rotation, and the other one is going to be the function that you're integrating. And so if you have horizontal axis of revolution, then we're going to have rectangles parallel to the x-axis here. These are parallel to the x-axis, so these are going to be horizontal rectangles. And these are going to be vertical rectangles. And it shouldn't surprise you that if you have vertical rectangles, you still have a dx. If you have horizontal rectangles, you still have a dy. So notice the new expressions, p and h. So the function p of x is the distance from the axis of revolution to the center of the representative rectangle. And again, we'll just call that p. It's rho, but we're going to call it p. And the function h is the height of the representative rectangle. So big idea here, shell method we use parallel to the axis of rotation. So, and shell parallel, it rhymes. So that you remember when to use the shell method. So let's look at this example here, or this visualization at least. So visualization of the functions p and h for the shell method for a horizontal axis of revolution, like the x-axis here. So if we draw a rectangle that's parallel to the axis of rotation here, so that touches the function over here on the right, and then we are going to have this distance here from the center of our representative rectangle to our axis of rotation. That's going to be P, but this distance that is the height of the rectangle right here is our f of y, is our height. So we have a vertical axis of revolution, like the y-axis here, x equals 0. Then we have vertical rectangles that are representative. Our height is going to be our f of x again. And our p of x is going to be our distance to our axis of revolution here, which is going to be our x value in this case. And in this case, it's just going to be our y value. It's not always going to be x or y, but lots of times it is going to be x or y. So let's find the volume of the solid formed by revolving the region bounded by the solid formed by, let's draw a picture here, y equals x minus x cubed. And the x-axis between x equals 0 and x equals 1, we're going to revolve it around the y-axis. So why did they choose x and 1? Because that's where it crosses the x-axis. This cubic function here, I factor out an x. Actually, let's factor out a negative x. It's going to be x squared minus 1, negative x times x plus 1 times x minus 1. So crosses at x equals 1 and x equals negative 1. And it goes down and to the right, and it goes up and to the left. And we're going to we can use some calculus here to find out exactly how far down and how far up it goes. But it does something like so. And we're interested in this bit here that's between 0 and 1. And we want to revolve that around the y-axis. Let me switch colors here to get something like pink. And so we want to make a rectangle that's parallel to our axis of rotation here, like so. And that makes a lot of sense to me to do that because we've got y equals 0 down here and y equals x minus x cubed up there. So we have 2 pi, and then x is going from 0 to 1. Yes, 0 to 1. We're going to have a dx out here. Then we have a p of x, which is our distance to our rectangle there, is going to be our x value times our function x minus x cubed. Notice there's no squared or anything like that in the shell method. So we're just multiplying by this x, which is this distance to the axis of rotation, times the height here, and we're going parallel to the axis of rotation for our rectangle from 0 to 1, have the multiplier of 2 pi on the outside. So 2 pi, 0 to 1, this is x squared minus x to the 4th dx, 2 pi, then we get x cubed over 3 minus x to the 5th over 5. From 0 to 1 is going to be 2 pi times 1/3 minus 1/5. And then those are all zeros. I'm not worried about them. 2 pi times 15 thirds minus 3. 5/15 minus 3/15 is 2 pi times 2/15 is 4 pi over 15. So now next example, let's find the volume of the solid form by revolving the region bounded by the solid. Using the equation x equals e to the negative y squared and the y-axis, so the region that's between them revolved about the x-axis. So first let's think what x equals e to the negative y squared is going to look like. So if we would graph this in the calculator, we would have to graph it as y equals e to the negative x squared, and you have to kind of turn the calculator on its side to see what it would look like. But you're going to get this. So here's the picture of it at y equals 0. This is going to be x equals 1 over here. So this is 1, 0. And at y equals 1, this is e to the negative 1. Like so. Is right there. And we have this nice curve right here. We're interested in a rectangle that goes between the y-axis and the function and is revolved around the x-axis. So there's our representative rectangle drawn in green. Our height function is going to be e to the negative y squared. Our p of y is going to be y. And so we're going to have v equals 2 pi, actually it's right down here, 2 pi 0 to 1 of y times e to the negative y squared dy. Let me show you the work for this. 2 pi. Your u is going to be your negative y squared. Your du is going to be a negative 2y dy. So this is going to be e to the negative y squared times negative 2y dy. And when we multiply by negative 2 on the inside, I have to divide by negative 2 on the outside. 0 to 1. So this is a negative pi. And then this is going to be integral of e to the u du. I'm going to change my u's here. So 0 squared, that's going to be 0. And 1 squared, that's going to give me negative 1. So I don't like my smaller limit being on top. I'm going to change my limits of integration here from negative 1 to 0 and change the sign on the outside. E to the u du, like that. And so that's going to be e to the u from negative 1 to 0, like that, is going to be e to the 0 is 1 minus e to the negative 1, be 1 minus 1 over e. And then this is times pi that was sitting out there. So pi times 1 minus 1 over e. That's what we have right here as our exact answer. And then this is our approximate answer right here. If we would type that into our calculator, we would get that answer there. So let the problem guide the method. Take a look and see whether it's easier to use vertical or horizontal rectangles, and see whether we're going to have rectangles that are parallel to the axis of rotation or perpendicular to the axis of rotation. And then remember, your formula for disk washer is based off of A equals pi r squared. And this is based off of S is equal to 2 pi r h. So you're going to have more variables in your shell method, and you're going to have a multiplier of 2 pi, but you're not going to have anything squared in your shell method. You're going to have one function here that's squared for your disk. For your washer, you may have big R squared minus little r squared, like that. So, all right. Draw your pictures, then choose which method you want. And next time we'll come back and we'll be comparing these methods, and we'll focus on problem setup and figuring out which method we want to use and why. So we may look at some problems and try and do them both ways and see which way was easier. We'll especially be looking for some problems like this last one that involves some U substitutions. So we'll come back next time and talk about 7.3, where we just generally talk more about the shell method and comparisons to of the two methods and when we should use each. All right, see you for the next video.